All right, it's 3 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Pretty good. Good to hear. All right, so today we're doing a big shift. So it's the start of the third week of our summer session. So up until this point, for the first 2 weeks of the summer, we've been focusing pretty much exclusively on ANSYS. So we've done our first three ANSYS activities, and basically everything we've talked about in the lecture have to do with how to set up things like the meshing, the boundary conditions, the material properties, all the good stuff. So all that's great, but part of this, the other part of EGME 410 is that we have to go over some theory as well, and so we're going to start that this week. So we'll start today. Tomorrow we are going to take a break and go back to ANSYS, just because I don't want too many ANSYS stuff, ANSYS things overlapping, and then we'll get back to the theory stuff on Thursday. Okay. Okay, so some announcements. And so remember, the midterm project is due this Sunday. I know quite a few of you have started working on it already, so I've already received a lot of questions over emails and through office hours today. All great. So I'm very happy you guys are looking at it and starting it early. If you haven't had a chance to start yet, I would definitely get started. The simulations themselves don't take too long to run. Especially if you kind of know exactly what boundary conditions you want to run in already. But there are inevitably going to be some issues or questions that you may have, and you want to make sure that you have time to answer those. Because I will say right now that this weekend is going to be very busy for me. I didn't plan it this way; I just couldn't get a reservation sooner than this. But this weekend is my son's birthday, so we're throwing and planning a party for him. So I don't think I'll be very available on this weekend to answer questions. So if you have questions on the project, make sure to try to get them to me this before Friday. Friday will be kind of the last day I'll be kind of available. But I'll try to find some time this weekend. Maybe just kind of be on my phone just to answer questions. But try to get a head start and finish before the weekend, just to make sure you have any questions that are answered. Okay. But again, the simulations themselves shouldn't take too long. I think you guys will probably spend more of your time writing the report, as is usual the case with most finite element studies as well. But I would say, try to at least get all your simulations done before the weekend. That way, in the weekend, if you have to, you can just focus on writing the report. Okay. Okay, and so with that said, I know tomorrow we are doing a new ANSYS activity. I'm not going to make ANSYS activity 4 due until after the midterm project, just so for this week, I want you guys just to focus on the midterm project. We do kind of have to keep the show going though, so that's why we're starting ANSYS activity 4 tomorrow. But my plan is to not have it due until next Wednesday, 11:59 p.m. Okay, so that way, after the midterm project is due, you still have a couple of days to do activity 4. Okay. All right, and so that's, I believe, all my announcements. Any questions I can answer before we get started for today? All right, question in the chat. So for the midterm exam, is that essentially what we're going to be starting learning today? Yes. Yeah, so the midterm exam is going to be on the Tuesday of week 5. So that's going to be 2 weeks from today. So that's going to be all on the theory stuff. So that's starting today. We're going to cover more theory stuff on Thursday and then early next week as well. Yeah. There's not too much theory that we're going over in this class, but the problems do take a while. And so that's why, the midterm exam for this class is kind of like a pseudo final. So I'm going to give you guys the entire 3 hours to take the midterm exam, not because the problems are particularly difficult. They just take a long time to do. So starting today is going to be all the theory stuff. Today is going to be what we're going to start to prepare you guys for that midterm exam. All right, any other questions before we get started? Okay, all right, so let's go ahead and get started. Okay, so topic for today is, again, a big shift compared to what we've been doing up until this point. But today we're going to be starting to discuss some finite element theory, okay? And so to do that, we're going to introduce something called the direct stiffness method for finite elements. Okay. right, so I know I've said this ad nauseum. I've said this, probably more times than it's almost like a broken record at this point. But finite elements is merely just a technique for solving differential equations numerically. Okay? So I think I've mentioned this at least once every day this summer, probably more than once. Um, But we haven't really talked about how this is done. Okay. Now, the interesting thing is that finite elements is not just one particular technique. There are actually different ways to actually implement the finite element type of analysis. Okay? And even among those different implementations, there are different variations based on, certain types of scenarios or certain types of situations or certain types of equations. And so finite elements is actually a very broad kind of topic to kind of discuss. Okay. So what we're going to cover in this class is what I would consider to be the very simplest implementation of the finite element technique, which is the direct stiffness method. Okay. Which, for this class, I think is very appropriate because, if we were to kind of go beyond this, then, it would kind of turn into a graduate level class, which we do have one here. It's EGME 541. So, if you were ever curious about diving further into finite element theory, that's the one that you would take, if you were to come back for grad school. But I have been getting a lot of questions from people that were interested in our blended program. So, I thought I would kind of mention that in case you do come back here for grad school. Okay. Now, direct stiffness is kind of funny in the sense that it's so simplified. It's so simplified in the fact that we actually aren't going to be dealing with differential equations at all. Okay. It actually kind of simplifies all those details out. But what you're left with in direct stiffness is what I would consider to be, all of the essential steps to doing a finite element computation. And so, I present the direct stiffness in this class not as something that is practically useful, which kind of seems very counterintuitive. But direct stiffness, I see it more as just kind of an illustration of the theory and the process of going through these computations. Okay, because even though when you use a software like ANSYS obviously is doing a much more sophisticated process in order to produce these solutions. It's still following these very basic steps that are involved in finite elements, which we can see in the direct stiffness method. Okay. And I do want to make a distinction here because we've up until this point in the class, I think we've already gotten accustomed to a certain other list of steps or a certain other process that's involved in running an ANSYS simulation, right? So I'm talking about kind of the process that we've run in ANSYS activities 1, 2, and 3. So in those activities, what we did was we established our geometry, we meshed our geometry, we applied boundary conditions, we specified which results that we wanted to see, and then we ran our simulation. Okay. So that's the essential steps required in kind of a practical point of view, right? As a user of finite elements. But if you were to kind of ask, or if you were to kind of look inside ANSYS itself and to see, what ANSYS is actually doing underneath the hood as you're doing these steps, that's kind of what I mean by this. Okay. So I make that distinction here where, what we're going to cover today and for the rest of the class today on theory is specifically on the FEA computation, okay? Which is different from the steps for running FEA simulation in ANSYS. And so, a little bit confusing, but I think kind of once we kind of get used to this process and we kind of, see what's involved, I think the distinction will be a bit more. Okay. So before we kind of get into the nitty gritty, I do want to list out those steps here. And so some steps do overlap with the practical steps, with the ANSYS steps that we're accustomed to. But there are some kind of additional steps which ANSYS kind of essentially hides from you, just because it's kind of unnecessary for a general user to see. Okay. Okay, so step one is the same. So step one is we're going to establish our geometry. Okay, which is the same as establishing our domain, right? So we have to have a subject, and so no matter how we approach our finite element simulation, we have to, know what we're simulating on. Okay. Step two, also very similar to our ANSYS processes that we need to essentially put a mesh on our geometry. But I'm going to be a little bit more specific here. In step two here, we're going to break up our geometry into elements that we can process. Right? Because what we're going to do in the direct stiffness method is kind of focus more on those individual elements and kind of work with those on a more close basis. I think, up until this point in the ANSYS activities, we've meshed our geometry. We've kind of just looked at the elements and we say that, oh yeah, there's 5,000 elements in this mesh, but we haven't really looked at kind of what the individual elements are actually doing and what computations are actually being done at that level. Okay. Okay. So step three is kind of where things deviate, or not really deviate, but this is kind of the start of the steps that ANSYS essentially hides from you. So step three is we need to compute something called an element stiffness matrix for every single element in our mesh. Okay. Right. So we're going to define what I mean by element stiffness matrix very soon. That's kind of the first subject once you get past this introduction here. Okay. Step four, after we compute all of the element stiffness matrices for all of the elements, we need to assemble them all together. Right. And so again, we'll kind of talk about what that process entails. But the result of step four is that we actually obtain just what I call a single global linear system. Okay. All right, and then once you do that, step five will sound familiar, but the way that we actually apply that to our calculations are going to be different. So step five is we need to apply our boundary conditions. Which, up until this point in ANSYS has just kind of involved this kind of clicking and establishing forces and fixed constraints. Through this direct stiffness method, you'll see mathematically how that actually works. Okay. All right, and then after step five, we need to solve. And I guess to be more specific, we're going to solve our linear system. And that will give us our result. Okay. All right, so if we kind of look at this, right? So first two steps, I think are pretty, we're kind of familiar with what that means. Steps 3, 4, and 5 are kind of what we're really going to focus on here. So these three steps here, right? These three steps are essentially hidden from the user, so you don't actually see what's going on. The only thing you really see is that ANSYS is thinking and kind of processing the result. But what we're going to do in direct stiffness is we're actually going to see kind of what those steps actually entail, right? So just so that you have an idea of kind of what the computers actually do. So as we kind of discuss the direct stiffness method, as we kind of discuss the different types of elements that are available to you in direct stiffness, you'll see the application of this kind of, essentially a three-step process, okay? Which again, is not anything that you would do in ANSYS, but, it is important to know, the nature of kind of how these computations are actually done. Okay. Okay. And so, this kind of step-by-step process, and especially steps 3, 4, and 5, you'll see me repeat quite a bit over the next couple of weeks, just because we're essentially going to be applying this exact same process, just with different types of direct stiffness elements. And so we'll be going over spring elements, truss elements, and beam elements. And if we have time, maybe frame elements as well. But typically in 410, we don't have time to cover frames, just because we got to get back to ANSYS. But that's essentially the plan for the next couple years. Okay. Okay. Any questions on this? Okay. All right. So first, let's start our discussion with the element stiffness matrices. That's kind of the new concept that we haven't really discussed at all. Okay. So what is an element stiffness matrix? So when you do a finite element computation, whether you're using ANSYS or whether you're doing a direct stiffness calculation, every single element in your system, we need to, or every single element in your mesh, we need to compute an element stiffness matrix. So whenever you produce your mesh, whenever you run a simulation, just know that every single element in your system has a matrix that's essentially computed for. Okay, that means if your mesh has 1,000 elements, that means there must be 1,000 matrices that must be computed. If your mesh has 50,000 elements, that means 50,000 matrices have to be computed as well. Okay, so the amount of matrices that have to be computed grows with the number of elements in your mesh, which also grows the cost of your simulation, which is a concept that we're quite familiar with up to this point. Okay. Now the purpose of this matrix is to basically have a mathematical representation of the relationship between a force and the response in that particular element. Okay, so what do I mean by that? So to kind of illustrate this, let's bring up an old friend. Okay, so hopefully you've kind of discussed how springs work. Probably hopefully in multiple classes, but at the very least probably in your physics class. So if we think about a spring, okay, so a spring is a very basic type of mechanical component, right? It has the ability to stretch and compress. Okay, right, and so kind of the most basic kind of relationship here is we have maybe a fixed wall here. Maybe our spring is attached to the wall, okay, like that. Right, so let's say that we're applying a force to the spring, okay, right? And so in this case, we have a tensile force that's being applied, so the spring is being pulled away from the wall. And so what we expect in this situation is that the spring is going to stretch, right? So maybe before we apply the force, the spring had some length here. So this L is kind of what we would describe as kind of the resting length of the spring. But then as a result of us applying the force, the spring is going to stretch by a certain amount. Okay? So let's say that, after we applied the force, our spring was elongated by an amount which we'll call it V. F right here, this is our applied tensile. Okay? So that's the general behavior of spring. And actually, most elastic structures as well. If you apply a force, then we expect the structure to deform in that way, just like we've done in our ANSYS simulations. Okay. Now for a spring, the only difference is that for a spring, we actually have an equation that can relate the force to its stretch length. Okay. Okay. And so the equation is we have the force, right? So we have F is equal to our what we call the spring constant for the spring. So that's what we often call this a symbol. We often give this a symbol K. Right, so the force is equal to the spring constant multiplied by the deformation of the spring, or okay. Right, and so this equation here, right, so this very simple, maybe you've known it as kind of the spring equation. It's kind of more canonical name is called Hooke's law for springs. Right, so very simply, we just have force is equal to spring constant multiplied by the deformation, the d. Okay. Okay. So why do I bring this up, right? And so, I just mentioned that, we want to cover this concept of the element stiffness matrix, and the element stiffness matrix shows a mathematical relationship between force and response. Okay. If we look at this very simple equation for the spring here, right? This spring here actually is a great illustration of that exact concept where we have a mechanical structure, we have a force that's being applied to it, and this equation here will basically tell us how that structure is going to respond. Okay. And so if you think about it this way, where the force obviously is going to be some applied external force. And so if you apply an external force to a spring, the way it's going to respond is that it's going to deform, right? And so the deformation amount d, whether that be elongation or compression, this is the response of the structure in response to that applied force. Right, so what we have here is a simple equation that relates the force to the structural response, okay? Now, our equation here, of course, does not involve just those two variables. The spring constant is there as well, okay? So you can think of that spring constant as a way to modulate the response, right? And so, the force that we apply is not always exactly equal to the deformation unless the spring constant is exactly one, right? That spring constant there is there to kind of modulate the response. Because you can definitely have springs that are stiffer than others or springs that are not as stiff as others. They have different spring constants. And so depending on the properties of the spring itself, different springs are going to have different responses. And so that's captured in the spring constant. Okay. Right. And so that spring constant is there to kind of illustrate the fact that whatever response that we get depends on the nature, depends on the material, depends on the size of the spring itself, which is illustrated by that spring constant. Okay. All right. So very simple equation, right? So probably an equation you've never thought more than 3 times about. But there you can see here there's a lot of really interesting information we can kind of glean, a lot of different interesting ways we can interpret it, which is going to help us with our understanding of the element stiffness matrix. Okay. All right. So it feels like I've been talking for a while. Are there any questions on anything so far? Okay, good. Okay, so let's take this concept and apply it to an element stiffness matrix as well. Okay, so if we take this exact same structure where we have an applied external force, we have the response of the system, and we have some way of kind of modulating that response, that kind of gives us our framework for defining our element stiffness matrix. Right, and in fact, I'll actually be a bit more specific. And so the element stiffness matrix plays the exact same role as the spring constant in the equation above. Okay? Because whenever you apply an external force to any kind of object, right, how that object is going to respond to that external force will depend on the properties of that object, right? It'll depend on its material properties. It'll depend on its geometry, right? Just like we've seen in our ANSYS simulations. And so the element stiffness matrix kind of encapsulates that information and puts it in a kind of mathematical way. Okay. And so the exact definition of the element stiffness matrix. The element stiffness matrix combines all properties of our element itself, including its material properties, including its geometry. Right? So our element stiffness matrix will combine all of the relevant properties associated with that finite element. And so the main ones are going to be your geometry and material properties. That's mostly what we're going to concern ourselves with in this class, but there are other factors as well. Okay. So it combines all these properties and gives a relationship in terms of how that finite element is going to respond to forces in a system of linear equations. Okay? And so that last bit there is kind of the most important, and that's kind of why we get a matrix at the end of this. Okay. Because if you recall from your linear algebra class, right? If we have a system of linear equations, right? So basically algebraic equations that have, our variables don't have an exponent greater than one, right? We can express that in matrix form, right? So for example, this has nothing to do with finite elements. I just want to kind of remind you how to get a matrix set of equations, right? And so let's say we have two equations and two unknowns, right? So let's say we have 5x1 minus 4x2 is equal to 3, and then 6x1 plus 7x2 is equal to 8, right? Right, so we have two unknown variables here. So our unknown variables are x1 and x2, right? And we have two equations that we can solve for those two variables, right? Now, for a simple system like this, you don't really need to put it in matrix form. You can just, solve one equation for x1 and then plug that into x2. That's a very valid way to do this. But, you can take any system of linear equations like this and express it in what we call matrix form, right? So this is just an aside, right? So this is kind of just showing you how matrix equations kind of work, right? And so basically, in order to put this in matrix form, we can extract all the coefficients in front of each equation, put that into what we call our coefficient matrix, multiply that by a vector of unknowns, and set that equal to a vector on the right hand side. Okay? So essentially, the matrix form for this set of equations is 5 minus 4, 6, 7. Okay? Multiplied by x1, x2 is equal to 3, 8. Okay. Okay. So that matrix set of equations is equivalent to our system of two equations, two unknowns. It just expresses it in a different way. Okay. Now, matrix form is quite popular. It is used quite a lot. Maybe not necessarily for small systems like this, but if you have, a lot of equations and a lot of unknowns, matrix form is quite nice. And it does, and a lot of linear algebra theory, a lot of linear solver methods are kind of based on this kind of matrix form. Okay. So the idea with the element stiffness matrix is that, our element stiffness matrix is actually going to play the role of this matrix right here. Okay. So the idea is it's going to be a matrix of constants, right? So those constants are going to be determined based on the geometry and material properties of that element, right? That's going to relate the response to the force that's being applied on that element itself. Okay. Okay. Good. All right. Any questions on this so far? Okay. All right. So how do we actually find the element stiffness matrices? Well, this is the part where we're going to kind of gloss over a lot of those details. So actually deriving an element stiffness matrix is actually pretty hard. And we do, and if we want to do this kind of in the more traditional way, that would require kind of more advanced math that I don't really want to get into in this class. So I think the only thing I'll say is that the derivation of these element stiffness matrices is quite difficult. It depends not only on the shape of the element, but also on the governing equations that we're trying to solve, right? So the element stiffness matrix for a static structural simulation is going to look different than the element stiffness matrix for a static thermal situation, things like that. And actually, as you get into more and more advanced finite elements, a lot of the theory of advanced finite elements is kind of centered around this idea here in terms of, how do we derive or how do we get expressions for these element stiffness matrices, okay? So we are going to simplify it quite a bit, and that's kind of where the direct stiffness method gets its name, because we're going to more or less directly compute these element stiffness matrices, kind of circumventing the entire process of the governing equations. But even then, it's still going to provide us a good illustration of the finite element process. Okay. So let's go ahead and move on to the next section, which is we're going to start with the most basic direct stiffness element, which is a spring. Okay, so there will be at least three direct stiffness elements that we're going to cover in this class. And so first one's going to be springs, which is what we're going to do today. We'll probably get to trusses, by the end of this week. I anticipate that. And then we'll probably cover beams sometime next week. Okay. Okay, so let's start with the spring. So you might be thinking, wait a minute, we've already discussed springs, right? We already have an equation that covers springs. We already have Hooke's law, right? And so how can we get an element stiffness matrix from a system that we already kind of understand? Well, the way that we kind of obtained Hooke's law here was, we had to basically assume that one side of the spring was fixed, right? And so the left-hand side of the spring here was fixed to a wall. That way, our displacement or our deformation was very easy to measure because we know one end is already going to be fixed, okay? But what if we loosen that restriction? So what if we basically take just an arbitrary spring with a force applied on each end of the spring? Okay, so let's look at a spring, but instead of a force being applied only on one side and the other side being fixed, let's say that we have a spring where we have a force on either side. They can have arbitrary magnitudes and arbitrary directions, and we're going to measure the deformation on each side of the spring as well. Okay. Okay. So you have a spring like this. It's more or less floating in air now. It's not being fixed to a wall. Okay. Let's say that we have a force applied on the left node, so we'll call that F1, and a force that's applied on the right node, F2. Okay. So those are external forces, and right now they are completely arbitrary. So I've kind of drawn them going to the right, just as a matter of convention, just because generally the positive x direction goes from left to right. Okay. But very easily we could swap their directions as well. And then in response, right, we're going to expect the spring to deform as well. Actually, let me keep it consistent with the previous terminology. Let's call it D1 and D2. Okay. So D1 and D2 are the arbitrary deformations of both ends of the spring. Okay. And so what we want to do is we want to derive an element stiffness matrix that's going to relate or give us a mathematical relationship between the forces F1 and F2 and the corresponding responses D1 and D2. Okay. All right. And so essentially, we seek a system that's going to look something like this. Right. So if we put it in matrix form, we have a vector F1, F2 is equal to stiffness matrix K multiplied by displacement vector D1 and D2. Okay, so we basically need to come up with two equations here, right? So we need to come up with an equation for F1 and an equation for F2. All right. So to basically derive this case, we're going to look at a very specific scenario. And that scenario is going to give us the blueprint for solving for these kind of mathematical relationships. Okay. So let's consider a very specific scenario for the spring. Let's consider a spring that's in static equilibrium with a tensile force applied on both ends. Okay. So similar to the initial situation above, but we're going to be a bit more general here. But we're going to have a tensile force applied on both ends, right? And because we are in static equilibrium, the magnitude of the forces applied on both ends have to be equal and opposite. Okay, so we have our spring just like this. Okay, and so what we're going to do is we're going to apply a tensile force. And so that means that we're going to apply a force that's stretching the spring over to the right on the left-hand side, or excuse me, on the right-hand side. And on the left-hand side, we're going to have our forces pulling it to the left. Okay. Those forces are equal and opposite. So, T on the left has to equal T on the right. Otherwise, we would have static equilibrium. Okay. And then what do we expect as a response? And so as a response, we expect the spring to elongate, right? And so we expect the left node to go to the left, D1, and we expect the right node to go to the right, D2, okay? Relative to its resting position. Okay, so we expect both nodes to kind of move apart from the center. Okay. So under this configuration here, we can basically compute the total deformation of the spring. Okay. And so, different from before, where before, we know that one end was fixed. In this situation, both ends are moving apart from each other. Okay. So the total deformation of the spring So the total deformation of the spring is basically going to be the sum of D2 and D1, right? And so, let's say D2, let's say that they both move an equal amount, right? So let's say they both move half an inch, right? And so D2 moves to the right by half an inch, D1 moves to the left by half an inch. That means the total deformation is going to be 1 inch, right? But, in this situation here, we do have to respect the directionality of our coordinate system, right? And so if we assume basically that the positive x direction is going to the right, right, as it typically is, right? That means D2 is going to be a positive deformation and D1 is going to be a negative deformation. Okay. So the total deformation then therefore is D2 minus D1. Okay. Then what we can do, right? So even though this spring here has multiple degrees of freedom, right? So we now have two degrees of responses here. We can still, the spring is still a spring, right? So no matter how we kind of dress it up, a spring is still going to follow spring rules, going to do spring stuff, right? So we can still use Hooke's law to relate the tensile force to the total deformation. Okay. And so the tensile force applied onto the spring, T, is equal to D2 minus D1 multiplied by, I almost forgot this, multiplied by K, which is the spring constant for the spring, which I forgot to note here. Okay. And so we'll assume that we know the spring constant of the spring, otherwise we wouldn't be able to do this calculation. Okay, good. And so with this here, right? So with this equation, right? We have a linear equation that relates the total deformation of the spring to the tensile force. Okay. Now the next step here is basically to take this equation and then relate that to this up here. Remember, we need two equations here, right? So we need one equation for F1 and another equation for F2. Okay, and so that's going to give us our matrix set of equations for the entire system. Okay. Okay, so what I'm going to do is I'm going to take this figure here and I'm basically going to overlay it with this one right here. Okay, because this figure up here with F1, F2, this is what I would call the figure for the general case. Okay, where F1 and F2 here are arbitrary. And then this situation here with the equal and opposite tensile force, this is a more specific case. Okay. And so if we overlay our convention here, we're on the left-hand side at node 1, we have F1 that's going to the right, and F2 is defined as going to the right as well. Okay. Remember, the way that we define F1, F2 and F2 were nothing more than just the forces that were being applied on the two ends of the spring. Okay. And we have that here exactly already. So, we're applying a tensile force T on both ends of the spring. Okay. The only difference here is that, the directions that we chose for the tensile force are different than what we chose originally for the general case. Okay, so we're going to take this equation here and relate it to So we're going to relate this general equation to our generic F1, F2 forces. Okay. And so based on this figure up here, right? Let's start with F2 actually, right? So F2 is going from left to right. The tensile force T at node 2 is also going from left to right, right? So that means that, if we relate our specific situation to the general one, F2 has to equal T. Because they're going in the same direction, right? Whereas if you look on the left-hand side, right? And so we look at the situation at node 1, T, we are applying a force with magnitude T on node 1, but it's in the opposite direction of what we originally defined. Okay? So that means F1 for the situation is equal to minus T. Okay? Has the same magnitude, but just opposite in direction. That's why we're putting that negative sign. Okay. So now what we can do is now that we have equations here for F1, F2, and we have an equation for T, right? Let's plug in for T into these equations. Okay, and so F1 is equal to minus T. And so we're going to have minus K D2 minus D1. Okay. And we have F2 is equal to positive K times D2 minus D1. Okay. Okay, so we're almost done. We're just about there. Okay. So I'm going to take F1 just because, I don't really like that negative out in front. Let's take that negative and just distribute it through the equation. All that's going to do is just going to swap D1, D2. So instead of D2 minus D1, we have D1 minus D2. And in fact, just to kind of make it a bit more clear, let's distribute the K also. I probably should have done that in that step as well. Okay. Right, so F1 is equal to K D1 minus K D2. Okay. And let's do the same thing with the F2 equation. So I'm going to take K and distribute it through the equation there. So F2 is equal to K D2 minus K D. All right, so now we have a system of two equations and two unknowns, right? So if we consider D1 and D2 to be the unknowns of our linear system, we can then extract the coefficients out into our element stiffness matrix. Okay? Let's take this linear system here, this very simple 2 by 2 system, and then let's put it in matrix form. All right, so we do that, we get F1, F2 is equal to K minus K minus K, K times D1, D2. All right, and so this matrix here, just like we've kind of previewed from before, this simple 2 by 2 matrix here is our element stiffness matrix for a spring. Okay, there's a long road to get there, but we'll use this in an example kind of right after this. All right, any questions on this? Okay, good. Okay, so this is really good. So one way that you can interpret this is, you can interpret this as kind of a more general form of our Hooke's law, right? So now we're not limited to just situations where our spring is fixed to a wall, right? We can use this elemental system here to consider springs that are not necessarily attached to a wall, right? In fact, we can even take it a step further. We can use our element stiffness matrix to analyze systems with multiple springs connected to each other. Which actually segues us perfectly into the next step in the finite element process, which is assembly. Okay. All right, because what we know is that a finite element analysis does not just consist of a single element. We have multiple elements, oftentimes multiple elements, right? So oftentimes we have thousands, millions of elements together, right? And so to do a finite element analysis is not just looking at one element individually, but multiple, right? And as you can imagine, the different element stiffness matrices from the different elements, especially the elements that are next to each other, they share nodes or they share edges, or in 3D they share surfaces as well. Their solutions are going to be linked together. Okay, and so the next step here is to say that if we have multiple elements, how do they interact with each other? How do we combine their element stiffness matrices? And so the next step in the process is basically determining or finding out how this influence occurred. In other words, how do we combine multiple elements again? Okay, so to illustrate this, I'm actually going to do an example. So it'll be kind of it'll be kind of like an example, but it'll be one where we kind of work through the theory and kind of use it to kind of illustrate stuff. Okay. Okay, so let's consider the absolute simplest situation here. Oh, sorry, question from the chat. So the question is, so basically what we did here is we find the element stiffness matrix for a free spring by relating it to a static spring, like the case of one fixed end, or excuse me, the case of one fixed on one end. Yes, exactly. Yeah, so we basically took our basic spring here, which has a fixed end, and we kind of generalized it to a situation where we have 2 degrees of freedom now, where both ends are free to kind of deform. Yeah. Okay, so let's look at the simplest kind of assembly of different elements where let's consider not one spring, but let's consider 2 springs connected to each other. Okay, let's have a fixed wall just because we do have to have a fixed constraint. And so, the rules of finite elements don't really change for direct stiffness. We still have to have a fixed constraint. Okay, so we'll have one spring that's directly connected to the wall. Okay, we'll call this element A, and it has a spring constant Ka. And then this is going to be connected to another spring, which we're going to call element B, and it's going to have a spring constant Kb. Okay. So we're not making any assumptions about the spring constants of these 2 springs. They could be the same, but in general they could be different. Okay. Okay, just like before, we are going to apply a tensile force. So on this entire system, we are going to have a force that's pulling the entire assembly to the right. Okay. And then what we're interested in is the response or the deformation of each of the nodes in our system. Okay. So we have node 1 that's attached to the wall. Okay. We have another node 2 that's going to be in between springs A and B. We have node 3 on the end, just like that. Okay, and then each of those nodes are going to have their own deformations. We're going to have deformation D1 at the wall, deformation D2, and deformation D3 at node 3. Okay. Now I know that node 1 there is fixed to a wall, and so just by definition of being a fixed constraint there, D1 has to equal 0. That's the definition of a fixed constraint. But for right now, we'll leave it general, and we'll see how we actually apply that boundary condition later. Okay, so this is a very typical, if not, quite simple finite element problem. And so what we're interested in solving for is we want to find out the deformation of each of the 3 nodes in the system. Listen. And so if we can find the deformations of those 3 nodes, then we know exactly how much each spring is going to be deformed. Okay. Okay, and so to solve this, we need to apply our finite element process. Okay. Right, so actually step 1 and step 2 of the process that we outlined at the beginning are already done for us. And so our geometry is already established. We've already broken this up into elements. In this case, each element is comprised of a single spring. Okay. Next thing to do is we need to compute the element stiffness matrices for each spring. So for spring A, element A, and spring B, we compute its element stiffness matrix. Okay. So we're basically going to follow this exact kind of formula up here. Okay. Except we're going to apply that to each of the different elements. All right, so we'll start with element A. So the only thing to note for element A here is that its spring constant is Ka. So the element stiffness matrix for this is going to be F1, F2. I said F2, but for some reason my finger said D2. Okay, the spring constant for element A is Ka, so we're going to have a positive Ka, minus Ka, minus Ka, positive Ka, okay, multiplied by the corresponding responses of each of those nodes, so D1 and D2. Okay, so that's element A. Let's do the same thing for element B, okay? Now we can tell right away, right? So since element B has a different spring constant, that means our matrix is going to involve that different spring constant as well, okay? So our matrix for element B here is going to be a positive KB, minus KB, minus KB, positive KB, okay? Right, so that part's straightforward. But, we also are going to make note of the fact that element B here, the nodes that it's connected to are nodes 2 and 3, right? Which is different than element A, right? Element A is connected to node 1 on the left, node 2 on the right. But for element B, it's connected to nodes 2 and 3. So we need to adjust for that in our equation. So instead of having a vector F1, F2, right? We're going to have a vector instead F2, F3. So F2, F3 is equal to positive KB, minus KB, minus KB, positive KB, multiplied by the vector B2, B3. Okay, right. So those are two separate linear systems for each of those elements there. Okay. Okay. So the goal for this problem is we want to essentially solve for the values of D1, D2, and D3, right? Because that'll give us what the problem is asking for. The issue here is that all of those variables are right now, they're kind of in separate linear systems, right? So we have D1 and D2 that are involved in the linear system corresponding to element A, and D2 and D3, those are in the linear system that corresponds to the element B. Okay. We can't really solve for these when they're in separate systems. And so the next step here is to actually combine these together into a single linear system, a single matrix set of equations, which will allow us to solve for all of the variables that we need. So essentially what we're going to be doing is we're going to be assembling everything, right? So we're going to assemble all the contributions from all the elements together, and that's going to give us a single elemental or single linear system where we can solve for D1, D2, and D3. Okay. Okay. So the way to do this is like this. And so to kind of start constructing your global linear system, you need to look at how many nodes are in your mesh. Okay. So in this mesh in particular, we have 3 nodes, right? So we have node 1, 2, and 3. That means our system is going to have 3 rows and 3 columns. So the size of your global linear system depends on the number of degrees of freedom in your mesh. Okay. For now, since we're just doing one-dimensional spring problems, the number of rows in your global linear system will just correspond to the number of nodes. But starting on Thursday, we're going to be looking at two-dimensional systems where each node can have multiple dimensions of deformation. And so we can have a deformation in the x direction, deformation in the y direction. Okay. So those situations get a little bit more complicated, but for now, just think of the number of nodes is equal to the number of rows. Okay, and so our global linear system is going to have a very similar form to our elemental systems, right? And so just like our elemental systems, we're going to have a vector that has all the nodal forces. So F1, F2, F3. We're going to have a large matrix portion here. So this is where our 3 by 3 matrix is going to be. And so since this is going to be a stiffness matrix that corresponds to the entire system, we call it the global stiffness matrix. Okay. And then this is going to be multiplied by our vector of responses here. D1, D2, D3. All right, but of course the question is, how are we going to fill in the 3 by 3 global stiffness matrix? Right. Okay. So the way we're going to assemble this is that basically each of the element stiffness matrices are going to make a contribution to the global stiffness matrix. Okay. All right, and the way we're going to do this is actually quite interesting. And so, if you look back at the previous step, right, we saw that for each of the elements, we took note of which nodes that element is connected to, right? So for element A, we saw from the mesh that this was connected to nodes 1 and 2, okay? Whereas element B is connected to nodes 2 and 3. Okay. So let's use that information to find out, and we're basically going to take each element stiffness matrix and insert it into the proper location into the global stiffness matrix. Okay. So let's start with element A. So we know element A is going to affect the result for our elements for nodes 1 and 2. Okay. And so if we look at the global stiffness matrix, and actually let me do this as well. Let me go ahead and write the columns in. Okay. So even though this is not a standard part of the global stiffness matrix, I like to write these in just to kind of help me do the assembly. Okay. So the first column is going to be the column associated with D1. Second column is going to be the column associated with D2. Third column is the column associated with D3. Okay. So we know that element A there is connected to nodes 1 and 2, right? And so if we make a box, right? So if you notice that the box there encompasses the first 2 rows and the first 2 columns of the global stiffness matrix, okay? In other words, we blocked out a 2 by 2, space inside the global stiffness matrix. Okay, that space is exactly where we're going to insert the contributions from element A. Okay, so if we put those in, okay, we basically have contributions that look just like that, right? So the 2 by 2 element stiffness matrix is literally just going to be just lifted up and inserted into the appropriate location in the global stiffness matrix. Okay. Let's do the same for element B. Okay. So element B we know is connected to nodes 2 and 3. So let's go ahead and look at our global linear system here. And let's box out the location that corresponds to nodes 2 and 3. Okay? So that's going to be the last two rows, so the D2 and D3 row, and the D2 and D3 columns. It's going to look something like this. Right, and so in the blue there, those are going to be the contributions from element B. Okay, so let's go ahead and add those in. But before we do, you can see here that we have one entry there that's overlapping the entry from element A, right? So the top left of the blue box is overlapping with the bottom right of the red box. Okay, so whenever you have entries in your global linear system that are overlapping like this, you're not going to overwrite it. Right? What you're going to do instead is you're going to add those contributions together. And so in that 2-2 slot right there, I'm going to use purple to kind of illustrate it, that this is a combination of the two. Okay, we're going to add those contributions together. And so we have a positive Ka that's coming from element A and a positive Kb that's coming from element B. Okay? All the other entries don't overlap, and so those remain the same. We have a minus KB, and a positive KB. Okay. And then any other entry in the global linear system that's not boxed, we're just going to put a 0. Okay. Okay. Those zeros do have significance, and by the time we reach the end of this example, we'll kind of go back, we'll kind of double back and explain what that 0 actually means. And actually, locating the zeros in your global linear system is actually a good way to kind of check your results. Okay. But this is kind of the basics of assembly here, right? And so after you're done computing all the element stiffness matrices, the next step is to assemble them like the following. Okay. All right. Any questions on this? Okay, good. So now that we've assembled this, right? So now we have a single linear system, right? Our goal is still the same, right? So our goal is still to solve for the values of these three here, right? So we still want to solve for D1, D2, and D3. But now what we can do is that now that we have this in a single linear system, we have essentially three algebraic equations for our three unknowns, okay? So we should be able to solve this system, right? Because that's what algebra basically tells us, right? So if we have the same amount of equations as unknowns, then we should be able to solve our system. Right. But of course, if you kind of know how we kind of do these things, I make a question, but then I answer the question right after. And usually the answer is no, right? And so in this case, we don't actually have enough. Okay. On the one hand, we have all of the force values on the left-hand side, right? So F1, F2, and F3, right? You can kind of think of these as kind of placeholders for forces, but we haven't actually applied anything there yet, because those are the generic variable names for the nodal forces on our system. Okay. So before we solve, we need to basically input forces for these placeholders. We can't solve a linear system if we don't know what the forcing vector actually is. Okay. right? But there's another issue actually as well, right? If you look at the matrix that we just created, and let me do this. Let me draw a line right down the diagonal, just like that. Right, so I've basically drawn a line down the main diagonal of the matrix. And what you should see is that our matrix here is actually symmetric, right? And so that means that if you look, if you consider that green line that I just drew as kind of like a mirror, right? Our matrix here has a mirror image on both sides. Right. So one thing about symmetric matrices, and this might have been something that was mentioned in your linear algebra class, but if you have a symmetric matrix that's governing a system of linear equations, you actually can't solve for the solution from there, right? Because what's happening is that you actually don't have you do have enough equations, but you don't have enough unique equations. So what tends to happen for a symmetric matrix is that you actually don't have enough equations that's actually under what we say under constraint. Okay. We're not going to get into the specifics of, condition number and determinants and things like that because that's kind of beyond the scope. This is not a math class. This is a finite element class. But just know that if you have a symmetric matrix, you actually can't solve that linear system just yet. Okay. So we're not quite done yet. And so before we actually solve for the solution, there is one more step that we have to do that's actually going to solve both of these problems at the same time, which is apply our boundary conditions. Which, if you kind of take a step back and you think of our ANSYS process, right? We couldn't solve any of our ANSYS simulations either until we actually applied the boundary conditions, right? The only difference now is that now we're going to see mathematically how those boundary conditions actually get applied to our system, okay? We'll do that after the break. Any questions on this before we head to break? Okay, all right, so let's take a break. So let's come back at 4:30 and then we will continue our lecture from. Yeah.
Well, also the sources for the midterm.
Yeah.
A lot of them were already finite element analysis of like problems. I'm not sure how to like get sources for like because I have computing size
Mhm.
to work on. It's just finding the sources for like why we need to see stuff like that. It's kind of hard to find sources to like.
Oh, I see what you mean. So like past reports are coming up.
Yeah.
Search. I would search kind of more generally. So you're doing which geometry? You're doing the piston rod, right? So I would just look up just piston rods in general, kind of what kind of situations that they're applied to, what kind of forces they're being applied to. So you can think of like specific applications.
Yeah.
So if you look at like an automobile engine, so that's a very common application. So I would look for those rather than
Okay, because I found like
reports.
a bit like the reports of the automotive, the aerospace, the hydraulic, the
Yeah,
pretty much
I know.
everything.
Yeah, I know. Yeah, I change the geometries each year just because I know that that's a thing. But yeah, I would look for more general sources. Yeah. Jason, sorry, I'm reading your question now, Jason. So the minimum factor of safety you can get and still have a safe part is actually one, right? So a factor of safety one means that whatever equivalent stress that you find matches the yield strength. So any factor of safety that's below one means that the part's going to break. That's a stress that's higher than the yield strength. So in order to basically what you could do is that you can basically do your project the same as we did activity two, where you can keep that the direction and location of that 425-pound load, but you can increase its value until you have a factor of safety of one. Yeah, and then that way you can find out, what the maximum load would be in that direction, in that location, that you can accommodate and still have um, a structurally sound system. Does that make sense? Oh yeah, yeah. So if you use if you use the material properties from within ANSYS, they might be a little bit different than probably what you look up online, just because ANSYS generally has alloys for these materials. I actually don't know exactly where they get the property numbers from, but if you want to use a very specific material that you're looking at, you may have to input it yourself. Yield strength, you would have to enter that under a different category. Don't know what it's called, but I think if you kind of look up kind of the probably it might be under like fail like category called failure. If you want to create your own material property, might be somewhere like that. Let's see. Oh yeah, yeah. Yeah, structural steel is nice because it has basically everything. And it even has strain life parameters as well. So if you want to do fatigue analysis, it's actually possible to do in ANSYS too. We'll probably cover fatigue analysis probably maybe last week. We're actually going at a pretty good pace, and so yeah, I think probably we'll have time after the exam to cover more niche features within ANSYS. Yeah, structural steel has basically everything. That's it's kind of nice in that sense, but you can't make practically you can't make every structure out of steel. That would be way too expensive and way too heavy. But in ANSYS, it's very convenient because it has all the data that you would. Okay, it's 4:30. Let's go ahead and get started again. I was checking my phone during the break. So my son's birthday party this weekend is going to be on Sunday, and if you're probably aware, the World Cup final is going to be this Sunday. So my son's birthday is going to be taking place during the World Cup finals. My dad made me go to the park yesterday and ask. He wanted me to ask the park first of all if they have electrical outlets so that we can make a projector and have a screen to watch the finals. And two, he wanted to ask if they have Wi-Fi so we can more easily stream the World Cup finals at the park. But I'm like, Dad, it's a park. I don't think they have Wi-Fi. I don't think they have electrical outlets out there. And And lo and behold, they don't. And so, my dad was kind of giving me some crap right now. So yeah, it would have been unfortunate, but probably that probably explains why it was easier to book this day. Because yeah, I think most people were going to be indoors watching the World Cup final on Sunday rather than being at the park. But yeah, it's kind of funny how it all works out. But hopefully this is only an issue once every 4 years. So yeah, next year probably is not going to be an issue. Anyway, okay. All right, so let's get back to finite elements. Okay, so we are almost done with the finite element process, right? And so what we've done so far is we have basically computed element stiffness matrices for every element in our system, which in this case is only two, right? And then we have assembled them together into a single global linear system, right? And so basically the idea is that, we want to have a single linear system that we can solve for all the unknown displacements, right? D1, D2, D3. And normally, normally for a problem like this, you would have actual numerical values for the spring constants. You would know the exact numerical value for the force, right? So this example that we're doing is kind of like an example in quotation marks because of course I'm not giving you values for this, although I think at the end I do have some values. So maybe that may be what I use for the second example. Um, you know, and so we're going to form the matrix set of equations here, but we aren't going to actually solve. But we're going to set it up until the point where if we did have numbers, we would be able to solve. Okay. So the next step in the process, kind of just like we mentioned right before we left for break, is the application of the boundary conditions. Okay. So we should be familiar with the boundary conditions, and so this is not the first time that we've seen them, right? So just to kind of refresh your memory, right? The reason we apply boundary conditions in finite element simulations is they are meant to model and emulate any external effects that are being applied onto our system. Okay. And what we've already discussed is that there are two types of boundary conditions. So we have constraint type and load type. So let's kind of refresh our memories in terms of what those mean. Okay, so constraint type boundary conditions, if you recall from our discussion a couple of weeks ago, constraint type boundary conditions directly specify the value of our primary variable. Okay. So whatever the primary variable is for our solution, our constraint type boundary conditions will be a direct specification of that. Okay. So that statement will have a bit more context here now that we're actually going through the math. And so you'll actually see what that actually looks like in our matrix system. Okay. And the other type of boundary condition are load type. Which at the time, we discussed, or the way we defined this was that a load type boundary condition is any such effect or external effect that's going to have an indirect influence on the value of our primary variable. Okay. So maybe indirect is not the best way to put it. And so loads do affect our results, right? So you apply a force, or you apply pressure. We know that's going to cause a change in deformation and stress and strain, right? It just doesn't do so directly. So there's no direct correlation. Say, the load is 5, that's going to cause a deformation of 5 as well, right? So indirect, what I mean by that is that, when you apply a force, it has to go through your governing equations in order for you to compute the corresponding response or deformation. Okay, that's different from constraint type. Where constraint type boundary conditions, basically wherever we apply constraint, we say the deformation has to be 0 at this location. Okay. Okay. So we have a constraint type boundary condition on our simple spring system, and we have a load type as well. So just so I don't have to kind of keep scrolling up and down, let me go ahead and draw the system here one more time. All right, so we have our two springs here. They are connected in series, and so one connected after the other. We have a force that's being applied on the right-hand side. And of course, on the left-hand side, we have our spring there that's fixed to a wall. Okay. So based on how I drew this and kind of based on what I've drawn here, you can see here that we have two boundary conditions. Okay. Okay. And so on the left-hand side, right, just like we've seen in our ANSYS simulations, a fixed support means that we have a constraint type there. Whereas the force on the right is going to be a load. So let's see how we specify these mathematically. So let's start with the constraint type, because that one's actually pretty straightforward. And so for a constraint type boundary condition, remember the way that we've labeled the nodes in our system is that the node that is attached to the wall there is node 1, right? I've gone ahead and labeled node 2 and 3. Okay. And so if we are specifying or we're basically constraining our system such that that node is going to be fixed, right? Basically what we're saying is that the deformation at node 1 has to be 0. Okay. So we can actually write a very straightforward mathematical expression to express this. Right? And so if the deformation at node 1 is 0, and if we look at our linear system, we have a variable here that we're already computing for the deformation of node 1, that's d1. Okay? That means the only way for this to be satisfied is we just make the equation d1 equal to 0. So that expression there fits exactly with our definition for a constraint type boundary condition. Because remember, for constraints, we're directly specifying the value of our primary variable. Our primary variable in this case is the deformation, right? And so by directly specifying or by directly applying that the deformation node 1 has to be 0, that is as direct as it can be. Okay. Okay. So all of that makes sense, right? So it makes sense that the deformation node 1 is 0, and that's mathematically how we express that. Okay. Now, the next question is, how do we take this very simple equation here, d1 is equal to 0, and how are we going to incorporate this into our global linear system? Because ultimately, when we solve our global linear system, we want that solution to reflect this constraint. Okay. Okay. So to do that, I'm gonna take this very simple equation and I'm gonna make it seem more complicated than it is. Okay? Right. So what I'm going to do is I'm going to take this equation and I'm going to modify it so that we can also include D2 and D3. Okay. How am I going to do that, you ask? Well, if we take those unknown variables and we multiply them by 0, it would be as if they don't exist, but at least we can include them in the equation mapping. All right, so in other words, I'm going to do this. And so I'm going to take D1 is equal to 0. Instead, write D1 plus 0 times D2 plus 0 times D3 is equal to 0. And in fact, we could be a bit more pedantic here and say that the D1 is multiplied by 1. Okay. All right, so normally you wouldn't do this, right? So normally you would not bother writing 0 times a variable because that 0 will just cancel it out, right? So this is normally what you do. If you have 0 multiplied by a variable, you just don't even bother. But then if we do that, we end up kind of right back where we start. So the reason I did this is because, if you look at our linear system, our global linear system here, I know it's kind of a mess at this point, but, just kind of try to focus on the first row. Okay. If we look at the first row in the system, actually, let me kind of clean it up a little bit just to make it a little bit easier to see. All right. Write it down. Okay, so that's a little better. So if we look at the very first row of our stiffness matrix here, okay. Remember, each row in the stiffness matrix and this entire linear system corresponds to a linear equation, right? That's kind of what we discussed before. This matrix is nothing more than just a representation of 3 equations and 3 unknowns, okay? The first equation being the multiplication of that first row and this vector here, okay? So if we were to multiply this out, right? So if we were to multiply out, we basically would take the coefficients of our global stiffness matrix and multiply it by our unknown vector, okay? We would get the following equation. Okay, so we have F1 is equal to Ka times D1 minus Ka D2 plus 0 times D3. So if you go back to our system, linear system, and multiply that row by the column, that's what you get. Okay. Now this equation that we are saying is representing our constraint is in a very similar form, although the left and right are kind of swapped, right? Okay. And so what if we do this? What if we take this constraint equation and kind of put it in a pseudo matrix form? Now we can't make a full 3x3 matrix because we don't have 3 equations, but we could put it into a kind of like a vector form. Vector-ish form. Okay, so what if we do this? And so instead of 1 times d1 plus 0 times d2 plus 0 times d3 is equal to 0, what if we do this? And so what if we do 1, 0, 0? Because those are all the coefficients, right? So we have 1 multiplied by d1 and then 0 multiplied by d2 and d3. Multiplied by the column vector d1, d2, d3. Okay. Right. And so the product of those two vectors, which, essentially you have a row vector multiplied by a column vector, that's essentially the dot product between those two vectors, okay? All of that is equal to 0. So this is interesting here, right? Because if you look at it this way, right, this kind of looks like a partial portion of our linear system. So then what if we take this, right? Specifically, what if we take this portion here, this very simple vector 1, 0, 0, and I guess technically this one as well, okay, 0. What if we take these things and actually use them to replace the first row in our global linear system as a way to specify and apply our constraint type boundary condition? All right, so let's see what that looks like. So I'm gonna write out our global linear system first in its kind of basic form, and then we're gonna do this replacement, and so just so you can kind of see it happening in kind of real time. Okay, so our global linear system right now is in the following state, right? So we still have our unknown forces here, F1, F2, F3, and that's equal to our matrix here. So our matrix is Ka minus Ka, 0, and then minus Ka, Ka plus Kb, right? So right in the middle of that matrix, that's the overlap spot. So that's where element A and B kind of overlap. Minus Kb, 0, minus Kb, positive Kb. And so that's multiplied by our unknown vector d1, d2, d3. Okay. All right. So what we're saying here is that, and so to apply our constraint type boundary condition, we're going to take the first row in the matrix where the first row corresponds to node 1, okay? And we're going to replace it by those two box expressions there. And so in the matrix, we're going to replace that with the row 1, 0, 0. Okay. Actually, let me go ahead and insert that down here. Okay. Okay, so we're going to be replacing this first row of Ka minus Ka and 0 with 1, 0, 0. Just make it all red. Okay. And then the 0 that's on the right-hand side, I know I have the side kind of flipped, and I do this every time, and I apologize. But that 0 is going to take the place of F1. Okay, so if we erase F1 here, put a 0. Right? Our constraint type boundary condition has basically hijacked the first row in our matrix here. Okay? But now if you actually multiply this out, just like we did before, right? We basically take this first row now, and we take the first row of the matrix, multiply by our unknown vector, and set it equal to the left-hand side, right? You'll see that we get exactly the application of our constraint type boundary condition, right? So this first row now expresses the constraint boundary condition. Okay. So our very simple constraint type boundary condition equation, d1 is equal to 0, has now become an entire row in the matrix. Okay, so that's how you deal with constraint type boundary conditions. So essentially what you're going to do is you're going to first form the very simple equation of what the boundary condition represents, and then use that to replace the row in the matrix that corresponds to that node. It's not multiple ones, actually, it's just a single one. Okay. And actually, it's not only just a single one, but that one is going to go in the place of the main diagonal. Okay, so in this situation, our constraint boundary condition is on the first node, and so that means our one is going to go. I mean, first of all, we're replacing the first row in the matrix, right? We're going to put zeros on every single entry in that row except for the main diagonal. And so the main diagonal for the first row is the first column. Okay. But if our fixed constraint boundary condition we're on node 3, right? So we would replace the third row in the matrix with all zeros, but then the 1 would go on the third column. Okay, so whichever is the main diagonal, that's where you put the 1 for your constraint type boundary condition. Okay. And then for structural simulations, the only constraint type boundary condition we will apply is a fixed support. And so that means that, on the forcing vector, we're always going to put a 0. Okay. But the part where you kind of need to worry about is where you're going to put the 1 for the constraint type. Okay. Any questions on this so far? Constraints. Okay, good. Okay, so that's constraint type boundary condition. So constraints are a little bit more involved, and then you actually have to replace a row. Okay. Loads are actually quite simple to apply. Okay. And so for load type boundary conditions, what you need to do is you basically just need to take note of which node the load is being applied onto, okay? And then just replace that value in the forcing vector of our global linear system. So for a load type boundary condition, you are not going to make any changes to the matrix. You're only going to make changes to the forcing vector. Okay. So for this problem here, right? So we look at our figure up here. We are applying a force to the right on node 3. Okay. That means we're basically going to look at row 3 in the matrix and only replace F3 with F. Okay. Okay, so we come to this point right here, right? Our force or our load is being applied on node 3. right? So that means F3 here is going to be big F. So we just basically replace the entry in the forcing vector. Okay. And then last step, for basically any entry in the forcing vector that we did not replace or that doesn't have any force or constraint acting on it, we just replace it with a 0. Okay. So in this case, that the only, we don't have any force or any load that's being applied on node 2. Okay. And so we're just going to put a 0. All right, and so with that, everything is set. Okay, and so by applying our boundary conditions, we kind of fixed both issues with our linear system that we had before, right? And so on the one hand, everything in the forcing vector is specified now, right? So we don't have any unknown F1, F2, F3 values. Now, granted, in this particular example, we don't have numbers, and so big F still is not technically specified, but that's normally something we'd be given. Okay. And if you look at our matrix here, we actually broke the symmetry of our matrix as well. Okay. And so the matrix here is no longer symmetrical, right? So by applying that Dirichlet boundary condition, we are good to go in that department. All right, any questions on this before we jump into another example? Okay, all right, so let's do one more example today, and basically you're going to see everything kind of put together. So we kind of took our time with this, just because I wanted to kind of explain every single step. But I think once you kind of see things full speed, I think things will start to come together really well. Okay, now there's not really any getting around it. These direct stiffness problems are quite lengthy, and so it does require a lot of writing in terms of writing the stiffness matrices. Assembling everything all together and applying the constraints and everything. So they do take a while. And so, that's why typically, you don't do finite element problems by hand out in the real world. So, for any real problem, you're going to be using a software like ANSYS. But again, the reason we're going through this theory is not to give you a technique that you're going to use in practice. It's just to kind of illustrate the theory, illustrate the process, just so that you have an idea of kind of what's happening under the hood. Okay. And the cool thing is that, after we kind of go through this theory, it becomes actually a little bit easier to kind of understand some of the error messages that ANSYS gives you. Okay. So ANSYS, I think, is a great software. The fact that they give a free version, I think, is brilliant. It's also great marketing. But, there is kind of a certain expectation in using ANSYS that you understand at least a baseline level of finite element theory. Because sometimes ANSYS will give you an error message where, it kind of just sounds like just gobbledygook. But, if you do understand a bit about the theory, then it makes a bit more sense. Sometimes. Sometimes they'll also give you an error message where, even if you understand the theory, you have no idea what's happening. And so that's kind of what I feel sometimes when I think some of you guys kind of have some very exotic ANSYS error. And it's not your guys' fault every year. ANSYS makes updates to their software. They just new issues just come up, and then I look at an error message and I'm like, I have no idea what that means. And so I'm probably doing the same thing as you guys are doing. But for some more common errors, understanding the theory will help you kind of troubleshoot the issues. Okay. Okay, so let's do one more example to kind of illustrate kind of this entire concept here. So this will be a slightly more complicated system. And so instead of 2 springs, we're going to have 3. Okay. So we have a fixed wall is again on the left-hand side. Okay. We have 1 spring attached to the wall. This is going to have a spring constant Ka. Okay. Then this spring is going to be connected to a wooden block Now, the wooden block itself is not going to deform, but the wooden block basically allows us to connect this to two other springs. Okay, so our last two springs here are actually going to be connected in parallel. Okay, so on top we have KB, and on the bottom here we have another spring KC. Okay. Right, so we have one spring that's in series with two springs that are in parallel with each other. Okay, so let's label the nodes in our system. So just like our previous example, we're going to have node 1 fixed to the wall. Okay. Our second node here is actually going to be the entirety of the wooden block because we're going to assume all of that kind of moves together. Okay. So node 2 is going to be has the combination of KA, KB, and KC all kind of move together. Okay. But the two right-hand sides of springs KB and KC are going to be free. Okay. And so for KB, we're going to say that the right-hand node there is going to be node 3. And for KC, the right-hand node for that is going to be node 4. All right, and then we also need some forces here. We also need some loads, right? And so we're going to assume that node 3 is going to be subjected to a tensile force. Okay, so we're going to have a tensile force F3 being applied on node 3. And then on node 4, we're going to have a compressive force. And so we're going to have a compressive force F4 acting on node 4. All right, and then just like the previous example here, we're going to compute, or we wish to compute, we wish to compute the values of the deformations of all of the nodes in our system. But in this case, we have 4 different nodes, right? So we have D1, D2, D3, and D4. Okay. And unlike the previous example, I am going to give you some numbers for this. Okay? Let's list out what the parameter values are. Okay, so for the parameter values, we have Ka first, because Ka is going to be 500 newtons per meter. Kb is going to be 100 newtons per meter. Kc is going to be 250 newtons per meter. And we have our two forces. F3 is going to have a magnitude of 100 newtons, and F4 is going to have a magnitude of 50. Okay. So our system now is a little bit more complex, but you're going to see that we're going to apply the exact same process here. Okay. So this will be kind of a good review of kind of everything we've talked about today. So we're going to go through, we're going to compute the element stiffness matrices for each of these elements here. We're going to assemble our linear system and then apply our boundary conditions in order to solve for these solutions. Okay. Okay. All right. So let's start with the first step. Right. So I guess technically, if you're referring back to our original, our original step-by-step process, the first 2 steps have already been done for us. So we already have our geometry. We already have our mesh in the sense that we already have our elements here. So the first actual step that we're going to do is we're going to compute our element stiffness matrices. Okay, so luckily for springs, this is pretty straightforward, and we actually have values for these spring constants now, which is nice. Okay. The only thing we have to be careful of is that, each of these different elements here are connected to different nodes. So we want to make sure that we account for that in our element stiffness matrices. Okay, so let's start with element A. So let's go back up to the figure here. So from our figure here, we can see that element A is connected to nodes 1 and 2. So let's go ahead and reflect that in our element stiffness matrix. Okay? All right, so our 2 by 2 element stiffness matrix is F1, F2 is equal to okay, Ka minus Ka minus Ka, D1, D2. Which in this case, we can plug in values for Ka because it was given to us in the problem. And so we have F1, F2 is equal to Ka for this problem is 500 newtons per meter. This is 500 minus 500 minus 500, 500, D1, D2. Okay, so let's do the same thing for element B. Okay. Right, element B has a different spring constant, and so we need to make sure that we account for that in our computations, but it's also connected to different nodes. Okay? So we go back up to element B here, we can see element B is connected to nodes 2 on the left and node 3 on the right. Okay, so this is going to be F2, F3 is equal to KB minus KB minus KB positive KB. I'm just going to write the value in. Okay, so KB in this problem is 100 Newton per meter. So 100, it's 100, that's 100, 100, multiplied by 2 and 3. And then we're going to do the same thing for element C. Now, element C is interesting. Maybe not at this stage, but when we go to the assembly, right? If we look at element C, we can see from the figure here that element C is connected to node 2 on the left. It's part of that wooden block, and then element 4 on the right. And so those are two nodes that are not consecutive with each other, right? So they don't come after each other. And so when we assemble, we have to be kind of very careful in terms of how we actually put that into our global stiffness matrix. Okay. Okay, so this is nodes 2 and 4. All right, so we have F2, F4 is equal to the value for Kc was what, 250? Okay. So 250 minus 250 minus 250, 250, okay. D2, D4. Okay. So those are our 3 element stiffness matrices for this problem. Okay? Elements A, B, and C. Any questions on how we got these values here? Okay, good. All right, so now that we have our element stiffness matrices, our next step is to do the assembly. So remember, the idea with assembly is to basically combine all of these stiffness matrices into one global linear system that we can use to solve for all of the unknowns. Okay. All right, so for this particular problem, we have 4 nodes, right? So one more than the previous one. So that means our global stiffness matrix will have 4 rows and 4 columns. Okay. Make sure to give yourself enough room here. You have F1, F2, F3, F4. And so our matrix portion is also going to have 4 rows and also 4 columns, right? So let's do the same thing I did for the previous one. So let's write the columns in as well, just so that we kind of know a bit easier in terms of what we're looking at. So we have D1, D2, D3, D4, 4 columns. And then for the rows, we have D1, D2, D3, D4. Okay. So we've created the space now. So now the next step is just writing in the appropriate values. Okay. So let's go element by element. So let's start with element A. And let's remind ourselves that element A is connected to nodes 1 and 2. Okay. So that's going to be the D1, D2 row and the D1, D2 column. So just like that. So let's go ahead and write in the values. So here we can actually put in some numbers. And so we have 500, minus 500, minus 500, and 500. Okay. Next, let's do element B. So element B is connected to nodes 2 and 3. Right, so that means we're going to go to the D2 row, the D2 column, so that's second row and second column, and the D3 row and the D3 column, so that's third row, third column. Okay. So luckily they're all in one contiguous block, right? And so element 2 is going to be these entries right here. So we're going to walk off that 2 by 2 space. And we're going to add those contributions. And so remember, any place that has an overlap, we're just going to add those together. Okay. So element B here, the spring constant was 100. So we have a plus 100, minus 100, minus 100, and 100. And then finally for element C is connected to nodes 2 and 4. All right. So that means we're going to modify the D2 row, the D2 column, and the D4 row and the D4 column. Okay. Now these aren't consecutive, right? So the second column and the fourth column are not next to each other because there's the third column and the third row that's in front of it. Okay. So this is fine, right? So you don't have to have the entries next to each other. You just have to make sure that you apply them on the correct row. Okay. So first, let's do the entry in the D2 row and the D2 column. Right. So that's going to be this one right here. So that spot there is actually quite busy. It has contributions from all 3 elements there. Okay. Right, so we're going to have a positive 250 that's being contributed from element C. Okay. Next, we have the D2 row and the D4 column, which is this entry right here. Okay. Right, so this entry here is going to be a negative 250. Okay. Next, we have the D4 row and the D2 column. So that's going to be this entry right here. Okay, so that one's also going to be a negative 250. And then finally, we have the D4 row and the D4 column, which is this entry right. That's going to be a positive 250. Okay, so essentially what we did was we took our 2 by 2 element stiffness matrix for element C and we kind of just split it up, right? So that they're added into the appropriate row and appropriate column. Okay. So you can see if we kind of merge these four things together, right? We kind of bring them up the middle, right? We have the same 2 by 2 matrix, right? So the entries themselves are the same. It's just that we had to kind of split them up just because element C was connected to nodes 2 and 4. Okay. And this is very common, by the way. In fact, in ANSYS, I would be very surprised if there were two elements that had entries that had all the nodes were kind of all next to each other in the matrix like this. That would be actually kind of strange. Okay. So don't be afraid to split things up. In fact, it's required that you have to do in some of these situations. Okay. All right, and then again, just like our previous example, any entry here that is not boxed, we're just going to put a 0. And so we have 6 zeros to input there. Okay. Oh, and one more thing. And where we have everything that's added here, we don't have to keep it like that. We can just supply the added value. Right, so we add all those things together, we get 850. Right, so you have 500 plus 100 plus 250, that is 850. Okay. Any questions on how we did the assembly here? Okay, good. So next step in this process is we're going to apply our boundary conditions. Okay. But before we do that, I do want to make a note here. Okay, so if you remember from before, right, when we first brought up the idea of assembly, I told you that these zeros in the matrix here actually do have some significance, right? So a 0 like this one here, this one here, this one here, this one here. Right? We have 6 zeros in this system. Okay. Now, before you move on to apply the boundary conditions, it's always a good idea to check the zeros in the matrix to see if they make sense. Okay. So what I mean by that is that when you see a 0 in the global stiffness matrix, that means that there is no element that connects the two nodes that are involved with the zeros. I'm sorry, I should be more specific here. By them, I mean connecting the two nodes involved with where that 0 is. Right? Because if you do everything correctly, right, and you set up your linear system correctly, any zeros that you find are going to be on the off diagonal, right? So they're not going to be on the main diagonal. That's not going to be necessarily true once we do 2D situations, which we're going to start on Thursday. But for one-dimensional systems, a 0 basically means that there's no connection in between the two nodes. Okay. Now, what do I mean by that? Right. So let me go ahead and zoom out here just so you can kind of see the matrix at the same time. Okay. Let's look at the first 0 that we experience here. Okay. So let's look at this 0 right here. Okay, so that 0 there is in the D1 row and the D3 column. Okay. So what that 0 there represents is that there is no element or no way that node 1 and node 3 are connected to each other. Okay. That's why there's a zero. So essentially there's no direct stiffness in between or direct connection between nodes 1 and 3. Okay. And that makes sense, right? So if we go back to our problem geometry, okay, node 1 is the one that's fixed to the wall, and node 3 is the one that's being pulled on the right-hand side, right? So, indirectly they're connected, right? And so, element node 1 is connected to node 2 through element A, and node 2 is connected to node 3 via element B, okay? So they are connected indirectly, or I guess, further steps down, but there's no direct connection between them. Okay? And so that zero there represents that fact. Okay? And you can look at every single zero in this situation here, and you can find the exact same pattern, right? And so for instance, if you look at the zero that's right next to it, the zero that corresponds to D1 and D4, right? So D1 row, D4 column, right? Node 1 and node 4 similarly are not connected to each other by an element in any way. Okay. Same thing with the zeros on the bottom there, right? And so if we look at the zero that's in the third row, D3 row, in the D4 column, that means node 3 and node 4 are also not directly connected to each other, which is also reflected in our geometry as well. Okay. So this is a nice check. And so, you don't have to do this in every single problem, but it's a good way to kind of check your work. Okay. Because I will say that once we start doing two-dimensional problems, things can get pretty hectic with this assembly here, right? And so you think a 4x4 system is big, wait until we're assembling these into a 12x12 system. And so things get really kind of hectic at that point. And so, you really want to check your work kind of as you go along for massive problems like that, just so that you don't run into any issues kind of further down the line. Because it gets harder and harder to find issues with these types of problems the further you get along. So, the more often you can kind of check your work, you're more likely to catch your mistakes and kind of fix them. Okay. Because the thing I find with these problems is that, I don't think these direct stiffness problems are that hard or that complicated. It kind of seems like a lot today just because we're kind of seeing it for the first time. But what you're going to see over the next few lectures is that direct stiffness is basically the exact same process over and over and over again. The only thing that's different is how you compute the element stiffness matrices. But the details in terms of how you assemble, how you apply the boundary conditions, they're all the same. And it doesn't help that it's very tedious. And so all of the mistakes that I see people make are just kind of very simple mistakes. You kind of maybe shift an entry over by one just by accident, right? Just because your matrix is just so big. Or maybe you just miss kind of adding an element in there or entry in there. And so they're all kind of very simple arithmetic errors. And so kind of the more you can kind of check your work like this along the way, the easier it is to kind of check and catch those things. Because a lot of times people will kind of get to the very end of the problem, they'll compute their solution, they'll find out it's completely wrong, and then they're kind of scratching their head in terms of where they made a mistake. And so at that point, it's much harder to find your mistake than if you're kind of checking it along. Okay. So that's why, you see me today, we're kind of really taking our time with these problems where, relatively speaking, the example we did earlier, this example here, they're very, very simple examples. But, I am kind of taking my time and kind of explaining every step so that, you have the ability to go and kind of, check your work throughout these problems. Because you don't want to get to the end and realize you made a mistake, because then it's really hard to kind of find where that mistake is at that point. Okay. Okay, but one way you can do that is, check your zeros and just make sure they make sense, right? One common mistake is that, when you're, let's say that you're inputting the entries from element A, right? You just kind of mistakenly kind of shift things over to the right by one just because the matrix is just so big. And you end up with a zero in a place like this, right? Which you're like, wait a minute, that doesn't make sense for there to be a zero there because, there's a connection between node 1 and node 1. And so you can kind of go back and kind of check that. Okay. All right. So that was quite the detour there, but let's go ahead and continue on. Any questions on the zeros in our global system? Okay. All right. So let's go and apply our boundary conditions. And so we have 3 boundary conditions to apply here. Okay. So first we have a fixed constraint on node 1. Okay. And we have 2 force constraints on nodes 3 and 4. Okay, so let's do the fixed constraint first. And so for the fixed constraint is on node 1. And so the way we're going to do that is we're going to replace this entire first row with that entry there. Okay. So let's go ahead and erase all the entries in the first row as well as F1. Okay. Right, and so when we apply our boundary condition, our first row is now going to read 1, 0, 0, 0. And then in place of F1, we're going to place a 0. So that change there is a fixed constraint on node 1. But remember, whenever we have a fixed constraint, we go to the row where that fixed constraint is being applied. Okay, we replace that entire row with zeros, except for the entry on the main diagonal, which for the first row is the first column. Okay, so we put a 1 there, and then on the right-hand side, or on the forcing vector, we put a 0 there as well. Okay. Okay, so that is our constraint boundary condition. Okay. We have two modes. So we have a tensile mode on node 3 and a compressive mode on node 4. Okay. Okay, so let's do the mode on node 3 first. Okay. Okay. So F3, we can see there is a tensile mode, right? Right, and so that means it's going to the right. And so we can say that node 3 is going in the positive x direction. All right, and so to apply that, we'll go back to our assembled linear system here. And so for F3, little f3, we're going to plug in the value for big F3, which is 100 newtons. All right. And then for the second mode, mode 4, F4, F4 is a compressive mode. But more importantly, this is a mode that's going in the negative x direction. Okay. So remember, you have to keep in mind which direction is the positive x direction. So in this case, the positive x direction is going to the right. Okay. If it's not stated to you, that's what's implied. So it's positive x is always going from left to right. Okay? That means F4 is going in the negative x direction. Okay. Right, and so when we input the value for F4 into our matrix, right, we need to make sure that we account for the sign. Okay. So F4, the magnitude of F4 is 50 newtons, but if we account for the direction, that means in our matrix here, we're not going to put in positive 50, we're going to put in a negative 50. So make sure you account for that, right? So make sure you account for the sign of the forces. Okay, and then finally, last step here is that for node 2, we don't have any loads or constraints applied to it, and so we just fill in 0 for that entry. Okay. All right, and so with that, we are done, right? And so we have our system here. It's a Technicolor rainbow abomination in a way, right? So I basically use every color of the rainbow here. But this matrix here is ready to supplement. All right, so we have 4 equations and 4 unknowns. And so technically, you know, I would say 4 equations, 4 unknowns is not cruel and unusual. And so this is one you could probably do by hand if you had a lot of time. But generally speaking, you know, I'm not going to make you guys solve these kind of huge linear systems. So 4 by 4 is okay, but you know, we're going to eventually see systems that are like, you know, 6 by 12 by 12, like I said, sometimes 14 by 14. And so those are kind of cruel to solve. And so usually once you get to this point here, right, this is the extent of all the manual work that you have to do, right? So I would only expect you guys to set up these matrix set of equations. Okay. Okay. Right, and so that's going to be for the exam as well, because the exam is not going to have any access to computers or anything like that. Okay. So for the exam, I'm only going to expect you guys to set up the equation, to set up the matrix. I think in my mind I said matrix, but for some reason I said equations. Okay. What you're going to see, so I'm going to assign the homework set associated with these problems probably after Thursday, because right now, we can't really do much. We've only done springs. Okay. In the homework, I am actually going to show you the answers, but in order to get the answers for the deformations, you need to compute it numerically. Okay. Now, I know some graphing calculators out there, if you have a fancy one, are able to solve linear systems. If you have one of those and you're familiar with that, that's great. Feel free to keep using it. But one thing I know that everyone has access to is math. So that's the last thing, or maybe one of the last thing. We might have more time to do to introduce trusses after this that we're going to do today. And so, manually, the only thing I'm expecting you guys to do is set up a matrix like this, but then to actually solve for the values of D1, D2, D3, and D4, you're going to need the help of either a graphing calculator that can do that or map, which I'm going to show you right now. But before we jump into MATLAB, are there any questions on anything that we kind of covered up until this point in the class? Okay, all right, so let's go ahead and jump into MATLAB. So this will be kind of your crash course into solving linear systems in MATLAB. Um, oh, and also, I'm so sorry, I missed your question. Um, Sorry, so this question was from half an hour, so for some reason I missed that. Okay, so question is, in the case that the block is rotating due to compressive and tensile forces, do we add those nodes to the end of the spring? So in this case, we're not assuming any kind of rigid body rotation. And so in reality, yeah, you probably expect this block to rotate, but we're only considering translational degrees of freedom in this case. Yeah. So we are going to account for rotation once we get to beams. But those are going to be kind of more nodal rotations. Yeah. But for kind of large body kind of deformations like that and rotations, then that's something you'd have to do computationally in most cases. But for this case, we're only looking at a purely one-dimensional system. Yeah. Yeah. I'm so sorry. For some reason, I didn't get a notification on the screen for that. Okay, all right, so let's go ahead and jump into MATLAB here. So let me go ahead and share my screen. Okay, I always forget to do this. I should have started MATLAB before what we did today. Okay, so the nice thing with MATLAB is that I know MATLAB can conjure up a lot of feelings, mostly negative ones, but for what we're going to use it for in this class, it's actually quite straightforward. So basically, all we have to do is we have to define a variable that represents our coefficient matrix. We have to define a variable that's going to define our forcing vector, and we're just going to do a very simple operation. We're going to use backslash to solve the linear system. Sign in. Notification. Okay. It's not my device, but it's whatever. Go. Okay. All right, so you're going to open up MATLAB here. Okay. Hopefully everyone has the coefficient matrix written down in their notes here. Okay. All right, and so it's basically just going to be a few lines of code. So we're not actually going to write a script. We're actually just going to be using this just as a very fancy calculator. Okay. So actually, if you look at my office computer, I always have MATLAB open, just because that's just the calculator that I use for computing stuff. Okay, so first thing we need to do is we need to define a variable that has a coefficient matrix. Okay. Okay, so usually I like to give this variable the symbol A. That's very traditional in terms of applied mathematics and linear algebra. Okay. So this is going to be our 4x4 matrix in our global linear system. Our question. So I did see this one. Sorry, Anas. So question is, we won't have to do MATLAB on the test, just the matrix set. That's correct. Yeah. So the exam is going to be closed. You're not going to have access to a computer on the exam. So of course, I'm not going to ask you to solve for these linear systems. You just have to set up the matrix. And so up until the point where you apply the boundary conditions, that's where I'm going to have you guys stop. Okay. So we are going to be applying or specifying our coefficients kind of directly into the matrix here. Okay. And we're going to do this row by row. And so if we look at the first row in our matrix, right? So hopefully everyone has the notes open. Our first row corresponds to our constraint type boundary condition. Okay. So we're going to write each entry in this row and we're going to separate them by a comma, right? So our first row is 1, 0, 0, 0, right? And then to go to the next row, we're going to use a semicolon. Okay. So semicolon goes to the next row. Then we're going to write the next row in there, right? So our next row is a minus 500, comma, 850, comma, minus 100, comma, and then minus 250, okay, semicolon. Then we have our third row. Our third row is 0, comma, minus 100, comma, 100, type, and then 0. Right? And then our fourth row is 0, minus 250, comma 0, comma positive 250. Okay. And then when you're done writing your matrix, make sure you use an ending square bracket. Right? You can put a semicolon at the end or not. Doesn't really matter because we're just using this as a calculator. Okay, so I'm just going to hit enter. And you can see now our matrix here, it has the exact structure and values that we want. So first row is 1, comma 0, comma 0, 0. Second row is minus 500, 850, minus 150, minus 250. Third row is 0, minus 100, 100, 0. And then fourth row is 0, minus 250, 0, 250. Okay. Okay. Next, we need to define our forcing vector, right? So we can give that the symbol F. Okay. We're going to use the same convention here, but we're going to separate every entry by a semicolon. Okay. Because our vector only has one column. Right? It's a column. So our forcing vector for this problem is 0, semicolon 0, semicolon 100, semicolon minus 50. Right? So those are all the forces and all of the constraints of our system in that one. Okay. Okay, and then we hit enter. All right, so once you have these defined, to actually solve this system is very straightforward. Okay. And so all you're going to do is you're going to type the name of your coefficient matrix, which is just A in this case. Okay. You're going to use a special symbol on the keyboard, which you can't really see, but it's a backslash. And so on a standard keyboard, it's the key that's right above the enter or return key. Okay. So it looks like that. It's not the division sign. So the division sign is a forward slash, which looks like that. Okay. What we want is a backslash that looks like that. And then after the backslash, you're going to put in the name of your forcing vector, okay, which in this case we chose F. Okay, so A backslash F. And so what that tells MATLAB is that we have this linear system. Here are our coefficients. Here's our forcing vector. Let's solve for the solution. Okay. All right, and then we hit enter, and then this gives us our solution. Okay. All right, and so with this solution, right, and so we have each of our variables here listed one after the other. So we have D1 is the first entry, which is a value of 0, which makes sense because that is where our fixed support is, right? So that means our deformation there should be 0. Second entry there is D2, right? And so that is 0.1. Third entry that's given here is our D3. Okay, so D3 in this case is 1.1. And then the fourth entry is our D4, right? And so basically MATLAB just basically lists them out to you in order. D1 is equal to 0, D2 is equal to 0.1, D3 is equal to 1.1, and then D4 is minus 0.1. I just wrote the same thing, just as a serial killer. Okay, but yeah, that's basically it. And so so you don't have to create a script or anything like that. You just kind of type it into the command window for MATLAB, and then it could solve linear systems for you just like that. All right, any questions on this? Okay. All right, it's a bit early, but also kind of late at the same time. So I don't want to start trusses just yet, and so we'll end a bit early today. And so when we come back tomorrow, we will do our ANSYS activity 4. So there is kind of a half lecture that goes along with it. And so we'll do that for the first half of class. And then second half of class, we will do ANSYS activity 4. Okay. But again, ANSYS activity 4 is not going to be due until next Wednesday. And so we'll do the activity tomorrow. But I expect, probably most people are not going to start it until after the midterm project is due. Okay. But I do want to do it tomorrow just so that it's out there, just so that we're kind of keeping pace. Otherwise, we're going to have a bunch of things kind of compressed at the beginning. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you guys all tomorrow.
Thank you.
Thanks. Our question, will there be a study guide for midterm? Yes. So I will put out a study guide probably next week. So midterm exam is not for 2 weeks. And so, yeah, we'll get past the midterm project first, and then we'll talk more about the midterm next week. And there will be a study guide for it. Okay. Thanks, guys. Question, will we be allowed to have notes? And so it'll be the same format as my typical exam. So you'll be able to bring up one sheet of notes. So that's 1 8.5 by 11 sheet on both sides. Good night. Thanks, guys.